may end up being the closest planet to us, Proxima b.
The James Webb Telescope, the largest and most powerful ever launched into space.
NASA has been pushing the boundaries of space exploration for years, launching telescopes into orbit to unlock the mysteries of the universe. But none have garnered as much attention and anticipation as the James Webb Space Telescope. Despite its astronomical cost and lengthy delays, the JWST has been hailed as a game-changer in astronomical observations. And now it has made a startling discovery that has sent shockwaves through the scientific community. The JWST has uncovered something that challenges our understanding of the cosmos, something so mind-bending it's been dubbed the warp bubble. But what exactly is a warp bubble? What has the JWST found? And most importantly, should we be scared? Buckle up as we delve into the tantalizing secrets unveiled by this cutting-edge telescope that may leave you questioning everything you thought you knew about the universe. The vastness of space holds endless wonders and mysteries, from distant galaxies to enigmatic black holes. As a species, we are driven by curiosity, eager to unravel the secrets of the universe both near and far. Are there other intelligent beings out there surpassing our own intelligence? Could there be a distant exoplanet teeming with life? However, the vastness of space presents a formidable barrier to human exploration, with distances that boggle the mind. Even the relatively closer red planet, Mars, requires an arduous journey through the inhospitable depths of space that takes over 5 months for volunteers of Elon Musk's colonization endeavor. And that's just the beginning. Imagine wanting to visit Proxima b, the closest known exoplanet to Earth. Located a staggering 4.24 light-years away, it translates to a mind-boggling 25 trillion miles. Such a feat remains a mere fantasy with our current technology. But does that deter our spirit of discovery? Not in the least. Despite the seemingly insurmountable distances, we have found ingenious ways to study these celestial objects from afar. Enter telescopes in space, our powerful eyes in the cosmos. While we may not be able to physically reach these distant wonders, we can send our instruments to study them and unlock their secrets, peering into the depths of the universe from a distance. And as incredible as the renowned Hubble telescope is, NASA never ceases to push the boundaries of innovation, launching satellites and finding new ways to harness the power of the universe's mysteries, including the elusive concept of the warp drive. The JWST is a game-changer, with unparalleled capabilities that allow scientists to peer further back in time than ever before, to study the very origins of stars close to the moment of the universe's creation. With its extraordinary vision, it is 100 times more powerful than the Hubble, enabling us to delve deeper into the history of the universe, reaching back to within 330 million years of the Big Bang itself. But how is the JWST able to gaze billions of years into the past? The answer lies in the journey of light. As distant starlight has traveled for billions of years finally reaches us, the cosmic time capsule reveals to us the secrets of stars from eons ago, from trillions of miles away. Even though some of these stars may have long since perished, NASA has already unveiled a tantalizing list of the first set of images that will showcase the awe-inspiring capabilities of the JWST. Among these captivating images is the Carina Nebulae, a stunning celestial cloud of gas and dust that lies roughly 7,600 light-years from Earth, adorned with brilliant stars that dwarf our Sun in size. And then there's Stephan's Quintet, a mesmerizing galaxy cluster located millions of light-years away, where 4 of the 5 galaxies engage in a cosmic dance, their shapes twisted by the gravitational forces of their celestial companions. But the awe doesn't end there. The JWST has also captured breathtaking images of SMACS 0723, a unique galaxy cluster that distorts and magnifies light from distant objects behind it, allowing telescopes to detect even the faintest and most distant galaxies. This is where the JWST truly shines, unraveling the mysteries of the universe in ways never before imagined. Yet, amidst all these astonishing discoveries, the concept of the warp bubble looms on the horizon, promising to revolutionize our understanding of space and time. Although delving into the intricacies of a warp bubble requires advanced mathematical knowledge, the implications of this groundbreaking concept are nothing short of mind-bending. So brace yourself as the JWST and its incredible capabilities are poised to reshape our perception of the cosmos and unlock new frontiers in our eternal quest for knowledge. Now, imagine surfing through space on a bubble, where time and distance bend to your will. That's the mind-bending concept of a warp bubble, a pocket of contracted space in the front and expanded space in the back, propelling you forward at speeds surpassing the speed of light, all without breaking the laws of physics. It's like a sci-fi dream come true. But what's the big deal about warp bubbles? Well, they solve a major issue with faster-than-light travel, time dilation. If you were to travel faster than light, everything outside your craft would age at an accelerated rate, while you could end up spending years on a distant planet while only hours pass for you. It's a heartbreaking consequence that could leave you saying goodbye to everything you love before embarking on your journey. enter warp bubbles, the heroes of faster-than-light travel. Inside the bubble, space remains unchanged, so time ticks normally. An hour spent traveling at warp speed would be just an hour for everyone else outside the bubble. It's like hitting fast forward on your cosmic adventure without leaving your loved ones behind. Fans of the iconic Star Trek franchise are no strangers to the concept of warp travel. Across 10 TV series and 13 feature films since its first episode in 1966, characters have zipped through the universe in powerful spaceships, exploring distant planets and communicating with extraterrestrial crews. The heart of it all is the warp drive, a fantastical knowledge that makes the impossible possible. Because, let's face it, the universe is a mind-boggling, vast and strange place, with cosmic distances that create seemingly insurmountable barriers. But with warp bubbles, we may just have a way to traverse the stars at speeds once deemed unimaginable. Now let's take a closer look at the elusive star Proxima Centauri, twinkling 4.5 light-years in the vast cosmic expanse. If you could travel somehow at the speed of light, it would still take you a staggering 4.5 years to reach that distant star. But alas, light itself serves as the ultimate speed limiter, putting a cosmic cap on how fast we can travel. Even with the fastest spacecraft ever built, a journey to Proxima Centauri would still take over 8,000 years, making staying close to Earth and its immediate vicinity the practical choice. However, the intrepid crew of the Star Trek universe didn't settle for such limitations. They discovered a solution that defies conventional physics and allows for long-distance travel in a fraction of the time, with the legendary torsion engine, powered by the awe-inspiring warp drive technology. By bending and twisting space-time, the warp drive can shorten the travel time to distant stars, making for a thrilling and mind-bending concept of travel. The concept of warp bubbles, proposed by the visionary physicist Miguel Alcubierre in 1994, has revolutionized our understanding of interstellar travel. Imagine compressing space and time in front of your spacecraft and stretching it out behind you, creating a bubble of warped reality that carries you to your destination at breakneck speeds. The real-world implications are astounding. For instance, with warp bubbles, a journey to Alpha Centauri, our nearest neighboring star system, could potentially be completed in just a month, as measured by clocks on board the spacecraft and back in mission control. It all started with Alcubierre, a brilliant mind who was doing his PhD research on Einstein's general theory of relativity when he stumbled upon an episode of Star Trek: The Next Generation. Inspired by the show's depiction of heavy masses curving space and time, Alcubierre scribbled down calculations on a scrap of paper, laying the foundation for a groundbreaking article that rocked the scientific community. In his visionary paper, Alcubierre outlined the concept of compressing space and time to create a torsion bubble, a radical idea that could potentially pave the way for unprecedented possibilities in space travel. However, there's a catch with Alcubierre's warp bubble. You see, the reality of creating a warp engine is far from easy. You can't just bend space aggressively with normal mass. You need something called exotic matter with negative gravity. It's a material that we haven't discovered yet, making the feasibility of warp drive questionable. Alcubierre's idea is to encase a spaceship in a bubble of flat space-time and twist space-time around it to achieve faster-than-light travel. But to make it work, we need either negative mass or negative energy density, both of which are purely theoretical and have never been observed in the universe. The only option currently available to us is negative energy, but even that comes with its own challenges. Generating negative energy requires an enormous amount of mass to create an imbalance between particles and antiparticles. When particles and antiparticles appear near the warp drive, the mass traps one of them, resulting in negative energy density. Alcubierre estimated that a warp drive with a 100-meter bubble would require the mass of the entire visible universe, which seems like an insurmountable hurdle. Despite these challenges, a recent accidental discovery by Harold White and his team, funded by DARPA, has brought a glimmer of hope to the warp drive enthusiasts. White and his colleagues were actually conducting experiments on the distribution of energy in a Casimir cavity when they stumbled upon a micro-nanoscale system that could potentially